Hello, my name is Uwe Artmann. I'm CTO of Image Engineering. IEEE-P2020 is the standard for image quality in automotive systems. It's the first international standard in this topic. So how can it help you? Let's have a look at that. So one category is the contrast performance indicators. That is something that is actually new. That has not been, there is no counterpart in existing standards, or that it's just a modification to existing things. So contrast performance indicators is something new, and it has shown in our daily experience here in our lab, but also with many customers that we work with, it has shown that it has a huge potential to be really a big help for the development process, not only for benchmarking, but also actually to work with the camera. So what does it do? So one of the contrast performance indicators is the CTA, contrast transfer accuracy. So you can see it like that. You have in an object, you would have two areas that form a certain contrast. And you want to answer, is my system under test capable to reproduce this contrast? Because if it fails for any reason, then that might be a problem. Because a lot of all detection algorithms for ADAS systems, they need to see some form of contrast, of object contrast. If the object doesn't form any contrast anymore, you cannot detect it. So what you see, so in real life, you have two objects. You have an object in the background, and then that can be simulated with a test target where you have these patches. That forms two distributions. So the distribution dark and the distribution bright. That is just like a histogram for these two distributions. And now you go pixel-wise, and from distribution A or distribution dark and distribution bright, you take one pixel there, and then you calculate the contrast between these. And then you do that repeatedly, over and over again. And that gives you a probability density function. Within this probability density function, you define bounds, and everything that is inside the bounds is good, that is actually reproduced. What is outside, that is rejected. So then we can create a single value that tells you what is the ratio of, in the probability density function, that values are inside my bounds and that are outside. So 100% means everything is inside the bounds. 50% would mean 50% is in, 50% is out. So the higher, the better. What is now the interesting thing, when we measure that, we cannot only measure for one contrast, we measure for many different contrasts. And that is something that we can provide. So then as a result, what you get from this measurement is a map. On the x-axis of this map, you have the average luminance. That's the average of these two patches. And then on the y-axis, you have the contrast that it forms. And then in color encoded, that is the contrast transfer accuracy, where we just said 1 is perfect. The lower the probability that you can actually distinguish these. So with this map, you can describe a lot of effects in the camera. So first of all, you have different positions. So you can have, that is like on the left of the image, you see there is the headlamps of a car and then a darker car in front of it. So that is a very bright, high contrast scene. So that's somewhere in the top or top right of my map. But then you have also some rubber pieces or tire pieces that is also in the lower left of the image. So that is something, a dark object on the dark road. So that is low light, low contrast, that's in the lower left. That's the very challenging part of imaging. So this way you can see where are the different areas that I should have a look at. But I also have some examples here where to look at. So here's the example where we have a road. Only the headlamps are active, but because I'm driving relatively fast, my camera system should look beyond the headlamps. So that means what I need to see is really low light, the low light performance of my camera. So for that, I have a look at the left region of my map. So what you see here is more like bluish purple. So that means, okay, I have a significantly reduced contrast transfer accuracy in this area. But that's where you have a look if you want to compare systems. How is my low light performance? Another aspect that you can have a look is a low contrast performance. So here, as the example, you enter the tunnel. It's not very dark. I mean, it's daylight, but these persons on the left, there's actually 3 persons. But because of the clothing and then something dark in front of a dark background, it's quite hard to see. So this is low contrast performance. And that is also very interesting to see from a camera. And that is more the lower area of the map. You see that I marked that here. So that is going from low light, low contrast to bright light, low contrast. And that's where you can see where you might lose some information. So that's where you want to look, can I really distinguish these low contrast objects? But then we also have an effect, especially when we have like HDR modes in a camera. So you see the car, the silver car is approaching my car that I'm driving from the sunny outside into the tunnel. And when I see these 3 images, when it's completely in the tunnel, I can see the car quite well. And if it's outside, I can see as well. But in the transition zone, it happens that it gets very noisy and I lose the contrast. So this is what is also sometimes called like SNR drop. So this is a transition zone between different exposures or different gain settings to create an HDR. And that's where you have a look at the certain contrast and then all the way above along the different luminance. So then if you have some peaks in there, that's exactly what how the effect can be described with the measurement. So that's extremely powerful to find out about the tuning of these configurations, because you have many different settings that you have to make to create this HDR, and that's easy to make a mistake there. So with these tools, you can very nicely see if it worked well or not. Another typical issue is the highlight performance. So you saw that in the previous video here, just a frame. One camera in the top has a highlight issue, so the clouds getting purple. While the car, the lower image is much better, so you have nearly the sun in the field of view, but there's no color shift and it can reproduce the clouds. So it's the same situation, it's the same brightness outside. And that's something that you can nicely see here on the right side. So that's the highlight performance. So you see, such map can give you a lot of different information for different things. So it's one measurement that tells you a lot of different things about your image. So how do we measure that? So the standard defines 2 different recording methods. So one that is called spatial recording. So we use for that the VLS, the versatile light system. So with that system, you can create 6 light sources that have a certain target. Each target has 36 patches. So that means that you have 218 luminances in the scene. And that means spatial, so different luminances are recorded on spatial different positions. That is, the spatial recording, so with 6 light sources. The contrast for that is the temporal recording, which, for example, you can also do over temperature. So for the temporal recording, you take a light source that you can control quite well, that gives you the luminance. So we use a Vega light source. So with that, you can control the intensity, the light luminance very well with this over a huge range. And then you put your camera in front of that, and then you take one image after another. So change intensity, take a picture, change intensity, take a picture. So this is then temporal, or in the time domain, the recording. Here, the nice thing is this is also something that you can easily bring into a climate chamber. So if you take our IQ climate chamber, you put the Vega outside of the window, the camera inside, and then you can perform all the measurements that we've just seen over temperature. So, for example, so what is the differences and pros and cons? So for the temporal recording, like on the left, you can measure CTA, CSNR, CNR, so different measurements from the standard with a small and easy setup. It's easy to integrate into your lab, or you could even do it on a bench or on a desk. The influence of flare from a lens is minimal. So you can perform this for yeah, or even with a cheap lens, it's no problem. But it requires a high level of control over the camera. So this works if you can, you need to be able to set the exposure and freeze the exposure. So no auto exposure, no auto gain control, auto white balance, or local tone mapping. That is not allowed if you do the temporal recording. And for flicker, you can just do a quick check, because to do a complete flicker test with this setup would mean, take far, far longer. So for that, there is the spatial recording setup. So the VLS with multiple light sources and then with test targets on top of that. So also with that, you measure CTA, CSNR, CNR with the very flexible setup. Additionally, you can also easily measure the MMP, a flicker measurement we're going to talk about later. With that setup, you can test all sort of images, including processed images. But you need to align well to mitigate flare. That's why we made it so flexible. So if you might need to align the light sources to your camera. So that's a big benefit, that it's so flexible so that you can do that, but that has an impact on that. So here's an example of a temporal CTA over temperature. I just talked about that, so that's definitely a possibility to park that. And you see here a sensor where we get into a huge, or where we get different behavior, of course, over temperature. So this is it's not optimized off-the-shelf camera with automotive-grade sensor. So we just took the off-the-shelf camera. This is not the best that this sensor can do, but we quite nicely see this is something that you could get from as the initial configuration from your sensor supplier. So there is some behavior. So we measure here the CTA for channel 1 to 4. In this case, it's an RGB camera with over the range of 50 degrees Celsius to 120 degrees Celsius. And what we see over temperature, so we have a reduced low light performance. So the more we heat up the camera, we reduce the low light performance. We get noise or contrast loss between the HDR exposures. So it gets quite significant the higher the temperature. And we have a bug-in readout. So there is a misconfiguration on the sensor. We know what it is, but it's quite interesting to see here. So if there is a bug in the readout, something that is easily to miss when you just go outside on the road, here in the data it shows up very easily, and so that you know, hey, there is something wrong with my measurement.